Hello everyone, welcome to the chapter Classification of Elements and the Periodicity in Properties. For today we will be observing the concept of electron affinity. Okay, now first we'll understand what is the concept of an electron affinity, how it is going to affect and what will be the variation when we consider the entire periodic table. Right? Now, in order to understand electron affinity, first we shall consider a simple outline of an atom. Let us say that this is an atom, right? So, if this is an atom, considering that this particular atom is taken in its gaseous state and provided that this particular atom is neutral in a sense, it has no charge. Okay, so in this case, what shall we do is, we are going to insert an extra electron. We are inserting an extra electron, right? So when we insert an extra electron to an atom which is taken in the gaseous state and which is neutral in nature, that time what occurs is, this particular atom is going to liberate out certain amount of energy. This energy which is liberated upon the addition of an extra electron to an atom, to a neutral atom in its gaseous state, we call it as electron affinity. Of course, this particular atom now, what we are going to get here, this particular atom is going to have a negative charge because we are adding extra electron to that. Now, therefore, this particular atom will carry a negative charge along with it, and therefore, we call now these as an anion. So, an ion is particular species which has extra number of electron, or you can say as extra negative charge, right? So, now what is happening here is the energy is getting liberated. Now, if energy is getting liberated, therefore, we are going to see that we are going to calculate this energy. Okay, and this particular energy is usually calculated taking into consideration of the unit as electron volts. Okay, now what shall we do is, we'll take one example in order to understand the concept of electron affinity in much better manner. So, in order to understand this, what shall we do is, we are going to take into consideration of oxygen. Okay, so oxygen, atomic number of an oxygen is 8. Correct? So therefore, what we will have, the electronic configuration as 1s2, 2s2, 2p4. Now, let us observe this condition in detail. Okay, now 2p4, in a sense, p orbitals, there are 3 types: px, py, pz. Right? Now, you are going to insert 4 electrons in this case. So, therefore, 1, 2, 3, 4. Now, please observe that we have a space to accommodate 1 electron here and 1 more electron here. That means the total capacity of P is actually 6. But right now, we have only 4 electrons in a neutral gaseous state of oxygen. Right? That means I can insert another 2 electrons. Now, let us observe as what will happen when we insert the electrons. So, we will be taking into consideration of oxygen atom. Let us say this is the nucleus, right? So, this is the first orbit, this is the second orbit. Now, what will happen? In the first orbit, we have 2 electrons. So, 1, 2 electrons. In the second orbit, we have total number of 2 plus 4, 6 electrons. So 1, 2, 3, 4, 5, 6. Right? Now, when we add an extra electron, okay, this is the first So we are adding an extra electron. So when we add an extra electron, what will happen is number of electrons into the system increases. As this increases, certain amount of energy is going to be liberated out. Okay, so as a matter, what is going to happen here is this oxygen atom is going to contain 1, 2, 3, 4, 5, 6, 7, 8. Now you have added one more extra electron to that, and that extra electron is here. So therefore, number of electrons have increased when we compare to that of number of protons in the nucleus. So therefore, now this is going to be an ion with an extra oxygen, which we have taken with an extra electron. In this case, whatever the energy that is liberated, try to understand, the energy is liberated, therefore we denote this as delta G is negative. Now, anything that liberates energy, anything that is giving out the energy, and the energy is going out of the system, we call this particular process as exothermic. Right? So, I would say as our first step in this case was an exothermic reaction because it is liberating the energy outside. Now, taking into consideration, like we will take the same thing, and what we will do is, this is your oxygen atom. Now try to understand that you are taking an oxygen atom which has one extra electron. We will take the same example here. That means we are going to have here 1, 2, 3, 4, 5, 6, 7, 8, and you have added one extra electron. Let me represent that with an yellow color here. Okay, so that is an oxygen in the gaseous state, okay, and carrying one extra electron, so therefore a negative charge. Now, in this case, what shall we do is, we'll try to add one more electron, as we have already seen that we have added one electron here, and one more electron can be added to the same p orbital. Now, when we add one more electron, now the thing starts changing in this case. What is the thing that is going to change here is, instead of liberating the energy, now this system is going to absorb the energy. You need to supply energy to this oxygen if you want to get this electron into the oxygen system, right? So therefore, the second step is not an exothermic. Now it is absorbing the energy, and therefore the system will now become as endothermic. Endothermic in a sense, it is going to absorb energy. You need to supply the energy to this particular oxygen now. So therefore, what will happen is, this oxygen, first orbit, this is our second orbit. So 1, 2, 3, 4, 5, 6, 7, 8. This is representing the first electron what we have added, and this one will represent the second electron. Now, question that arises is, of course, I'll complete here, energy. Now, in this case, the energy that what we are going to have is going to be positive. Now, when it is positive, that means the system is absorbing energy. Okay, question that arises is, why in this case is the oxygen ion is absorbing energy while in the first case it was giving out energy? Now, we need to understand that when we have added an extra electron, this electron causes electron-electron repulsions. Now, it has started to cause a repulsion because of negative charge electrons and already the electrons which are present in the oxygen atom. So, negative repulsions. Now, in order to overcome those electronic repulsions, and plus you need to add one more electron to that, then you need to invest some amount of energy. So therefore, the second step, the second electron enthalpy is going to be as endothermic.
Okay, so the first case was an exothermic, second case is going to be an endothermic, right? Now, let us get into details about this. So, what will happen is, when we observe the entire periodic table, okay, so at the end what we have is the noble gases. Now, noble gases, what will happen to them is the electronic configuration is completely packed. Okay, when we observe the electronic configuration, we'll understand that it has a configuration of Ns2, Np6. So this condition is called as the completely filled orbital configuration. Okay, so therefore, now this system cannot accept any electron. It cannot accept no matter what we do. So therefore, in such cases, what is going to happen is, here, the electron enthalpy is going to be taken as 0. Affinity is going to be completely 0. Okay. While that of alkali metals have an electron affinity ranging from 1 to 0. Okay, in the terms of electron volts. Coming forward, there are few elements such as beryllium and magnesium. If we observe that there are certain elements wherein the electronic configuration is somewhat like Ns2. Okay, so the innermost orbital is completely filled and there is no more electrons outside. So if it is Ns2 type of system where the electrons are completely filling the s orbitals, again this cannot accept any electrons. So once the capacity is already filled or it's almost up to filling that capacity, it cannot accept any electron. So in such cases, the value of electron affinity is going to be as 0, right? Now let us observe what will happen if the condition is something like a half-filled electrons, okay, half-filled orbitals. So in case if that is the condition, something with respect to nitrogen and phosphorus. Okay, so in such cases where we have electron configuration as Ns2, Np3. Now these are half-filled. Okay, exactly half-filled atomic orbitals. So in this case, it is not going to readily accept any electrons. So what is going to happen? We need to see that when we add the electron in case of nitrogen or phosphorus, as it is already half-filled. If it is half-filled, it's more stable. Remember this? If it is half-filled or if it is completely filled, it's already more stable than the rest of the elements. Now, if we try to add the electron to these, what is going to happen is the amount of energy that is going to come out is actually very less. Okay, so therefore, here, less electron affinity values. This is what we get in this case. Okay, so now what shall we do is we'll see what are the other factors that can affect electron. Okay. Coming towards what are the factors that are going to affect our electron affinity. The first prominent factor which affects the value of electron affinity is going to be as the atomic size. Now, we are looking at the atomic size. Now, try to remember. Electron affinity, what it is going to be that the electron is going to enter into the system, and as it enters into the system, the energy is going to be expelled out, right? So it all depends upon how better is our nucleus is going to accept the electron. Okay, so as the atomic size, so can I say as the atomic size as the atomic size increases. Okay, as the atomic size increases, can we say that as the atomic size increases, the distance from the nucleus, the distance from nucleus to the outermost shell or the outermost orbit is also going to increase. As that increases, attractive power decreases. As the attractive power decreases, then electron affinity value is going to decrease because it is all related with respect to our nucleus. Right? So what is happening? As the atomic size increases, the distance right from the center of the nucleus to the outermost orbit is going to increase. As that particular distance increases, attractive power goes on decreasing. As the attractive power decreases, the electron can easily come inside, it can stay there, and the amount of energy that is going to be liberated is very, very less. So, smaller the atom, more is going to be the electron affinity. Larger the atom, less is the electron affinity. This is how it goes. So, therefore, when we observe the trend in our periodic table, so what is going to happen in the periodic table? As the atomic size is going to decrease along a period, right? As we go along a particular period, what will happen? The atomic size decreases. If the atomic size decreases, then the value of electron affinity is going to naturally increase. When we go from the top to the bottom in a particular group, that time what is going to happen is the atomic size is going to, of course, it's going to become larger and larger. As it becomes larger, it is directly affecting the distance from the nucleus. As the distance from the nucleus goes on increasing, electron affinity goes on decreasing. So therefore, atomic size increases, electron affinity value decreases. But there is one particular exception. The exception is about the atom fluorine with respect to chlorine. If I say with respect to this condition, that means fluorine should be, this particular fluorine should be more electron affinity. It should have the more value of electron affinity, right? But that is not the condition here. It is because when we take a look into the fluorine, that time the atomic size of this particular fluorine is very, very less. Now first, let us try to understand that the fluorine has 9 electrons. So electronic configuration for this one will become as 1s2, 2s2, 2p5, right? So in such condition, in this condition, what is going to happen? First, 2 electrons, let's add 2 electrons. 1, 2. Next case, there are 2 plus 5, 7 electrons. So 1, 2, 3, 4, 5, 6, 7. Now in this case, what is happening is the electron density in this particular manner is concentrated in a very, very, very less space. The concentration of the negative electrons, the negative density is concentrated in very small space. So therefore, any incoming electron, whenever we try to put up any particular electron in this case, this electron is not accepted, rather it is repelled back. Due to this, the electron affinity value of this particular condition, that is a fluorine, is less. Remember, the electron affinity value of fluorine is therefore less when we compare to that of chlorine. So, one most important thing is the most electronegative or having affinity value. The particular atom having the greatest electronegative value, that is electron affinity value, is going to be fluorine. Remember this particular point. that is about the chlorine. Correct? The second factor which is going to affect is going to be the nuclear charge. Now, nuclear charge is nothing more than how effectively can our nucleus attract the outermost electron. How strongly it can attract the outermost electron, and that is called as the nuclear charge. Okay, so what we can say is, higher the nuclear charge, more strongly it is going to see that the outermost electron is going to be attracted. More stronger it is going to be attracted, that means more amount of energy that is going to be liberating out. So therefore, higher the nuclear charge, higher is the electron affinity value. Right? Coming towards the last factor which is going to affect, that is called as the shielding effect. We have already seen what is a shielding effect. Now, in order to understand the shielding effect once more in proper manner, what shall we do is we will take into consideration of a particular atom like aluminium. Okay, so aluminium, Al, atomic number is 13. So electron configuration becomes as 1s2, 2s2, 2p6, 3s, 2, 3p1. Okay, so 10, 12, 13. Okay, so what we will do is, we have aluminium, so electrons will add, so therefore we need complete number of orbitals, that are 3 in the space. So we have 3 orbitals, we'll start filling them with electrons. So in first case there are 2 electrons, 1, 2, next case there are 8 electrons, 1, 2, 3, 4, 5, 6. 7, 8. And the last case there are 3 electrons. 1, 2, 3. Right? So now, what will happen is the shielding effect. The shielding effect is an effect which is produced by inner orbital electron. Inner orbital electrons are these. These are inner orbital electrons. Once the inner orbital is perfectly filled, what it will do is, it will try to reduce the effect of this nucleus on the outermost electrons. That means, this attractive power of this nucleus is compensated in this particular region. And thus, it becomes very difficult for this particular nucleus to effectively attract the outermost electron. Here, the efficiency is going to decrease. As the efficiency decreases, the outermost electrons are not that perfectly bonded or not that perfectly attracted towards nucleus. Correct? So therefore, whatever the electron that we add in such kind of conditions, it is going to see that the electron will enter inside, but the amount of energy liberated is going to be very, very less. So this is the third condition. The third condition is about the shielding effect. So what will happen is, greater the shielding effect, lesser is the electron affinity value.